is Bill Licea-Kane. I work with Qualcomm, and I actually work for a small subsidiary of Qualcomm called Qualcomm Innovation Center. Yes, there I am. And I'm located in the Boston area. If you know the Boston area, I'll actually work in a place called Boxborough, Massachusetts, with a G-U-H, O-U-G-H at the end of it. And I've been volunteering with the Kronos group for years on the different graphics standards. So we're talking about render passes and subpasses today. So I wanted to start with, apologies to Prince Hamlet, words, words, words. Go back to the source of the great bards who wrote all the specifications, and I'll just read through what a render pass is. A render pass represents a collection of attachments, subpasses, and dependencies between the subpasses, and describes how the attachments are used over the course of the subpasses. The use of a render pass in a command buffer is a render pass instance. Terrific. What's a subpass, though? A subpass represents a phase of rendering that reads and writes a subset of attachments in a render pass. Rendering commands are recorded in a particular subpass of a render pass instance. So, with apologies to the bards, we are concise, we are precise, we aren't necessarily very illuminating with these definitions. So let's take another brief view. The way I always like to think about it as an application provider. So subpasses are just a bunch of rendering tasks that are taking place in some order. Each one of the subpasses has inputs and outputs, and there are dependencies between the subpass. So in this particular crude example that I'm showing, you've got subpass 0, which is writing to a depth buffer, subpass 1, which is now has that depth buffer as a read-only depth buffer and writing to a color buffer, and then finally subpass 2, which takes that color buffer and puts it into final presentable form. All right, so that's one other view of it. Now, from an implementer's point of view, render passes and subpasses are something slightly different. A render pass is an object that encapsulates the state I need to begin a render pass later on when I'm doing the command buffer recording. Also, coincidentally, the render pass, a subset of that data, has enough information so that when I create the pipeline object or when I create the frame buffer object, I know what you want to do with that. Similarly, the frame buffer object is enough state in there so that when I come around to begin render pass, I have all the information I need to begin recording the render pass without spending a lot of time during render pass, during command buffer building to bring things in. So I'm going to go, and so how many people have a fair amount of exposure to the Vulkan API already? Can I see a show of hands? All right, and how many people are brand new to the API? All right, so for the people brand new to the API, the first few API entries, I will walk you through them. Unfortunately, I will then start running. The nice thing is the pattern is fairly similar, so once you get the first ones, the later ones parts of the API will seem a little bit more straightforward. Don't get stressed about needing to know everything about how to set these things up right now. I'm going to hit the highlights of what you need to know and some of the difficulties that we have. I'm going to go through something similar to that simple example render pass that I just showed, and talk in particular about known limitations. We know that it's not as useful for most applications, and explain why the limitations are there currently. I'll explain a little bit more about dependencies and self-dependencies, and then finally give you some effectively hints and kinks about how you might use this API. So to create a render pass object, so in Vulkan in general, you have calls to create an object. You pass in the device that you want the object to be created on. You pass in a structure, which is create info, an allocator that's optional for you that you could use to allocate host memory or track host memory. And then it will return to you the render pass object. And this is consistent for all of the different create object APIs. So let's take a closer look at the create info for render pass. So here's the create info for render pass. Again, semi-consistent with Vulkan is the first couple of things in all of the create infos is a structure type, which just is effectively an enum that tells you what structure I'm working on, and a pointer to next. Pointer to next gives us the ability to extend that structure in the future or in the present in some cases. And then flags that typically go along with the objects. In this case, in the unextended Vulkan, there are no flags, so it's a reserved field. You set it to 0. The attachment counts. So render passes are a collection of image view attachment locations. And there'll be from 0 attachment locations to n attachment locations that you can have. And you need to describe what it is that you'd like to attach. So let's take a look at the attachment description. Primarily, you'll get the flags. And there is a flag in this particular one. The attachment may alias. And there are a number of different reasons in Vulkan where an image view might alias with another image view. Could be that you're passing into 2 attachments the same image view, so they're both aliasing with one another. The underlying sub-resource the image views are pointing to could be overlapping with one another, or the memory allocated to the overall object might be aliased with one another. And this is the place where you tell the render pass that that might be the case. And then the format, which is just the bucket load of all the different favorite textile formats that you might need to worry about. We need to know how many samples are going to be in the attachments. And then the load ops, store ops, and the layouts. Now the load op, you have a choice of either preserving the contents from before, loading it. You can clear the attachment, or you can don't care the attachment. The way to think about it is if you have an image that you want to preserve the contents of as you're coming into the render pass, you need to have the load. If you want it to be cleared to a known good value, depth buffers would be a typical one. You use a clear with a clear value. The don't care means I don't really care what value is, but use some sort of fast clear technique on the buffer, and we'll go and make that happen for you. The time that the clear load ops take place is somewhere between the beginning of the render pass instance and the first use of the actual input attachment during the render passes or subpasses. Similarly with store ops, you tell it at the end of the render pass what you would like to do. Either store the results so that they're going to be left off into the permanent storage, or don't care, which means they may never ever show up outside of the render pass subpass instances themselves. And the time that the load ops will take place will be either sometime between the time that you last used it in the last subpass, or at the end of the render pass instance. And finally, the layouts. Now, with Vulkan, you have different ways of laying out. Think of the underlying image view has a opaque view of the image underneath of it. It might be semi-transparent with a linear format. It might be completely optimized with some sort of optimal format. And then I can also give you additional hints about where you want to attach this to make it most optimal. So for example, for render passes in particular, you'd be looking at setting it up as a depth stencil attachment, optimal depth stencil read-only optimal, or color attachment read optimal. And now we're going to go into the subpasses. So we have all of our attachments, and now we have n subpasses, and there'll be at least one subpass in every one of your render passes, but up to n minus 1 subpasses. So we'll have to go through and describe the input attachments, the color attachments, the depth stencil attachments, and the preserve attachments. Now, because the Stanley Cup has been on, I came up with this semi-bizarre analogy. Think of all these attachments as your team that's sitting on the bench. And the coach comes out and says, okay, I need you and you to be color attachments. I need you to be a depth attachment. I need you to be the input attachment. And you guys, I want to preserve you. You're going to go into the next shift. You're going to be sitting in the preserve attachments. And so each one of the subpasses, you're taking your team, all of your attachments, and sending them in and out on the ice during the actual render pass itself. It made more sense when I was watching the Bruins for some reason. You can also, if you leave off one of the people on your team, you can send them to the dressing room, which is if you don't have them attached to anything in one of the subpasses and you don't leave them in the preserve attachments, they're gone. They're now undefined for the remainder of the render passes. And then the aspect rich. So I pointed to the extension. So in 1.1 we extended the render passes. We had a little tiny glitch. On depth stencil inputs, the aspect was depth and stencil. So when I wanted to read from it, what did I want to read, a depth or a stencil? So here's the structure that we pass in so that now you can actually tell me, do you want depth or do you want stencil? That's what this one did. And then finally, the dependency counts. Now, there might be a number of dependencies. An individual subpass might have multiple dependencies with other subpasses. So let's go into the subpass dependency structures. The source subpass and the destination subpass tells you my source subpass is who I am dependent on. My destination subpass is who I am. The one limitation is the valid usage is the source subpass almost always have a lower index than the destination subpass. If you go outside of that, you're not part of valid usage and you get undefined results. This prevents you from sending us an acyclic graph. Now, it actually doesn't prevent you from sending us an acyclic graph, unfortunately, because these are validity cases. So if you go through the validity tools, that'll catch that you're sending something that's not an acyclic graph. But runtime Vulkan, you could send us an acyclic graph, and all bets are off about what happens next. The source and destination masks, stage masks, just tell you what stage everything is dependent on. And that will make clear with a little bit later. And then the access masks tell you where you want to have things on in this pass. So coming back to the words, frame buffers represent a collection of specific memory attachments that a render pass instance uses. And the way I would think about it is at the end of us creating the frame buffer, we know everything we need to know to be able to set up the render targets. In fact, we know more than we need to know in order to be able to set up the render targets. And I know that's a source of frustration for ISVs, and we'll talk about that a little bit later. So going a little bit more quickly, we're going to create the frame buffer, give you the create info. You're going to pass in the render pass that we just created before. You're going to tell me how many attachment counts are going to be in the frame buffer, and the width, height, and layers. So all these things are attachments that are for image views. So here's creating the image views. Again, really quickly now, I'm going into the running mode now. Create info. I need to know the image that it's related to. Get to that in a moment. And the view type. And the view type, 1D, 2D cube, 1D array, 2D array, or cube array. Obviously, for frame buffers, you're talking about them being typically 2D, 2D array, and cube array. And then the component mapping. And then the sub-resource range. The sub-resource range is just out of the home large image, which might be a 3D image, 2D image, or 1D image. What slice of that, what sub-resource in that is the actual image view from? So the image object, we're going to create that. Create info. Again, the flags that tell you what kinds of usage, both the create flags and the image type, 1D, 2D, or 3D. It's just an array of bits. In 1D array, 2 array, 3D array that is opaque. And the one thing to look at in here for the create bits, possibly not too much interesting there. The extent and the image tiling, whether or not it's optimal or linear. And then the image usage flag bits. The transient attachment bit is probably the one hint for you on render passes that you'll want to pay attention to. If you know that the underlying image is always going to be transient, you can then allocate lazily allocated memory for it. And that tells us that you will never have defined results of that image after you exit from a render pass instance. So it's only defined between you can't load it because it's a transient image. You can only clear or don't care the contents of it. At the end of it, you can only don't care the objects of it. And in some implementations, we might even be able to get away with not creating the memory itself that backs up to it when you lazily allocate. Although, to be honest with you, most people who do the lazily allocate the backing store for you at that time anyway. So it's not going to save you memory, but it will save you some guaranteed memory of traffic. You don't have to worry about spilling back and forth. And now we finally get around to, during the command buffer building, you're going to actually begin the render pass begin, pass in the render pass begin info, and we're going to pass in the render pass object that we've created, the frame buffer object that we created, a render area, which is just some subset of the frame buffer that we're going to be rendering to in this render pass, and then the clear values that go along with that. Subpass contents, you have two ways of putting subpass contents into a render pass or a subpass. Either inlining it in the main command buffer, so all of your commands end up from begin render pass through to the next render pass, next subpass, you're building it in the main command buffer, or you can execute to a secondary command buffer. Each individual subpass, you have your choice of whether or not you want to do the everything in the top level or everything in the bottom level. So the first subpass, you might do everything is executes. The second subpass, you can do inline. The third one, you can do everything executes, and so on and so forth. So you get a choice per subpass. And the same thing happens. So here's the same thing with the next subpass contents. All right, now here's the wart in all of this, and this is why most of you don't like this. The subpasses in a render pass all render to the same dimensions. The fragments for the pixel, XY layer, in one subpass can only read the input attachment contents written by previous subpasses at that same XY layer location. So I'm going to go to my example now, and with apologies to Prince. So tonight I'm going to render like it's 1999. So this would have been fantastic a decade or two ago, but we've moved on. So for this simple example, I'm going to have a Z-only subpass. Hey, I remembered Z. FP16 subpass and tone map. And tone map in the crudest possible terms, where the app is set the transfer function. It's no automatic gain control. Because I have that restriction of I only know what my own pixel is, there's no way for me to know what the whole frame is. So I've got some kludgy mechanism to set the exposure control. One kludgy one that I would not suggest you do, but it's certainly among the possibilities, would be always set your exposure based on the last frame, because you have the contents of the last frame at the beginning of the subpasses. But don't do that at home. So I've got the 4 different attachments that I want to have. I've got the depth stencil with 4 samples. I've got the RGBA 16, a nice deep HDR color buffer. I have an S-norm RGBA 8 multi-sampled buffer, and then finally one sample S-norm buffer. My first pass will be the Z-only pass. And I will be attaching only the depth buffer and the stencil buffer. And I'm only going to be writing to the depth, so I'm going to do depth stencil attachment optimal on that. The second pass is the FP16 subpass. I will be attaching the color attachment now, and I will clear that. And I want it to be color attachment optimal there. And now I'm going to also transition the depth buffer to read-only optimal. So I started off with a depth stencil read-write buffer. Now from here on out, I'm doing read-only buffer. And so possibly I get a little bit of performance gain from that. And then the tone map subpass, I will attach the prior image to the input attachment as color attachment optimal. The S-norm buffer as a color attachment optimal as a writing, and then finally the single sample buffer that I'm going to resolve to. And notice that the depth buffer is now no longer in preserved contents or anything else. It's gone from the field. He's off in the locker room at this point. Now the dependencies on this one are somewhat rare and somewhat simplified. The first subpass, I start off with a cleared Z buffer. I have no dependencies on anybody outside of me. So often you'll find the first subpass has external dependencies, and you can look in the spec for that a little bit more. But this one, I'm going to set my second subpass has dependencies, my subpass dependencies, my first subpass has subpass dependency, has the dependency on the 0 subpass, the Z subpass, Z-only subpass, and my subpass is the FP16 subpass. The prior source stage, I wanted to make sure that all the late fragment tests have completed, and that's when the depth buffer got written. And then I don't want to start my destination mask until the early fragment tests begin, because that's the first time I'm going to be reading from the depth buffer that I've now installed as a read-only depth buffer. And my attachments are going to be, the source went from a depth stencil attachment write to a depth stencil attachment read, all right? And then the second subpass, the last one in the set, the FP16 subpass, the crude tone mapping, is going to read in the HDR buffer and write out the SNOR buffer, and transitioning everything that way. Now, the frame buffer needs to know the contents of the render pass, but it needs to know a subset of it. And in fact, the things that we need to know at pipeline creation time and at frame buffer creation time happen to be the same subsets. We actually don't need to know the load ops, the store ops. We don't need to know the layouts at all for the attachments when we're creating the frame buffer and the pipeline. So this is where you'll see the part of the spec saying, I need a compatible render pass that's provided, but I don't necessarily need the render pass that is provided. And then the subpass is the same sort of thing. I don't actually need to know the layouts, but everything else about it has to be identical to be a compatible render pass. And then the dependencies have to be identical all the way down the line. All right, the frame buffer takes the full set of the render pass dependencies. And then I'm going to set up the image views and images. So things that I kind of think of when I'm thinking about setting up the render pass is how deep I want to look through the chain of objects for the actual metadata that I want to take a look at the image. Mutable format might be something that I find useful as an implementer. And most importantly, though, the transient image flag is something that I might find interesting as as an implementer to be able to try to optimize which things go into the fastest possible memory. So here's the grossly simplified example I showed at the beginning. The dependencies are just subpass 1 to subpass 0, subpass 2 to subpass 1. The input attachments are shown as the dots before the shader circles, and the outputs are attachments are shown as the dot afterwards. Now this is really what it would be like if we were somewhere in this millennium. Because the common thing to see is some sort of bitmap chain reduction in the middle of your final image processing. And we only have access to the immediate pixel above us, so we can't do that. It would seem to be something that would be making life a lot better for you, at least get down to a couple chains down the bitmap chain without having to store all the information. Often the global information that you need for some of these algorithms is a reduced resolution of the main one as well. So there's some nice ways of hacking things out and get you a little bit closer. So dependencies and scopes on render passes. This is one of the things that's kind of nice on both desktop and on mobile, on the render pass features. So all the pipeline barriers and other barrier instructions in Vulkan have to do with prior scope and following scope. And the dependency scope for subpasses are the contents of that subpass. So in this case, I have subpass 0, which is dependent on nothing at all in this particular set of subpasses. Subpass 1 has a self-dependency, and so I can put barriers inside subpass 1 to itself, but I have to have declared that there are self-dependencies on that subpass for that to be a valid operation. Very common for these things to do on the subpasses with self-dependencies are things like a barrier for a prior read or prior write hazard, particularly one that's by region or by that single pixel. And then subpass 2 and subpass 3 both have dependencies that subpass 4.2. And subpass 3 happens to have its own subpass dependencies as well. So the only things that have to be done before subpass 4 is executed is the contents of subpass 2 and subpass 3. Subpass 0 could be scheduled last. It could be scheduled first, but it doesn't matter. These can be issued out of order from the implementation. And then the only places that you actually get defined ordering is within these limited scopes. And so just making sure that subpass 2 could happen after subpass 3 as well. So just because 2 of them are dependent on the same destination pass doesn't mean that they have to go in any meaningful order. So some recommendations. One of the things that we've seen typically that people try to throw everything they can into their frame buffer. It's the equivalent of bringing every hockey player that's ever played hockey to your rink. You want to select the people that you actually want to play. Please, no Uber frame buffers. The load ops and store ops are low-hanging fruit for desktop and mobile. So just go ahead and use them. Only use clear command attachments when you have to clear in the middle of a subpass. That's the best way of thinking about those. And try not to clear outside of render passes and subpasses if you're going to be using that resource as either an input attachment or a color or a depth attachment. One thing that I think is also low-hanging fruit is gather independent work items that happen to be same resolution images into a single render pass. And that way we can schedule the different subpasses in any order and possibly be able to not block on waiting for the load op or the store op to complete. When you are able to, and I know it does show up a few times, it might only be 2, but when you're unable to find a by-region dependency of 2 subpasses, that's a really good thing to go ahead and take a look at. And then finally, keep your expectations realistic. You're not going to get massive amounts of performance out of this, typically. You're probably not going to be bandwidth limited, power limited, or performance limited by the loads and stores from the render targets. But anytime you don't read and write something, you're saving power, you're saving bandwidth, you're possibly saving performance if that happens to be your bottleneck. So just try to grab it. The way I look at it is keep it simple, pocket the change. Don't stress out that the change is only a few cents. Any questions? Yeah. So from the commands that go into you say next subpass, then begin building up the command buffer. Let's say I have 5 draws writing to a surface. Then I have a self-dependency that says those 5 draws have to be completed before I can do the next 5 draws. So that's the self-dependency within the subpass. I need something earlier in my subpass to be done before I can proceed later on in the subpass. The subpass dependencies within subpasses, though, are restricted to simply all the operations inside the subpasses. Yeah.
Subpasses that have no dependency among them, can I have them executed on different command queues? Or
well, so if you place them, all right, so if you're submitting a render pass into one of your queues, so whether or not there'll be hardware queues in there or not that can run in parallel or not is an implementation question. But you can't have subpass, a render pass can't be split across multiple queues.
okay.
You choose which queue you're going to be going to. All right, well, I had to remember something. So I have memory problems sometimes. Oh, the next talk is about Vulkan memory management. It will be by Jordan Logan. Thank you very much.